Hi, Chapter 1, Sample Question 1, application of a direct application of normal and shear stresses in a real life engineering problem. So if we do have a steel bar embedded in a concrete and we just want to uh, take it out by a outward pulling force, we do need to know what is the sufficient length to prevent that force. So again, if a steel bar is sticked out from a concrete block, we want to know how much friction or how much length is needed to cancel out the pulling out force. And we have that in many engineering problems like balconies, cantilever beams, and different kind of frame and structures. So let's attempt some uh, problem for that. So if a steel bar is embedded in a concrete block like what we see here, we want to calculate the sufficient length in order to cancel out this pulling out force by friction of between the rod and the concrete material. So, and we are working to find out a relation for sufficient length and a parametric relation, and that should be in terms of normal stress sigma AL and bonding stress between two materials, concrete and steel bar, and that is bonding stress of definitely in terms of shear or tau friction between the two surfaces, and definitely based on the diameter of the bar itself. So let's see how it works. So when the part of the bar is inside or embedded in concrete block and you try to pull it out, a drag force in opposite direction of your pulling force is work all around the pyramid of your cylinder, and that's the friction or shearing force. So for shear, our area is nothing but pi times dl. So all around the our circle is pi times 2r is our area, and likewise our force would be the pulling out force should cancel out the or the force would be equal to shear acceptable shear times the appropriate area, which is pi dl. And in the other on the other side we do have a tension, a pulling force which applies to the cross-sectional area which is shown here, and that's nothing but pi d squared over 4, a quarter of pi d squared, and again the force is equal to sigma acceptable allowable permissible times pi d squared over 4. So if we equalize these two terms, 1 equal to 2 gives us the only unknown, and that's nothing but the sufficient length of a steel bar to prevent it from coming out from the concrete block. And that's nothing but sigma acceptable times diameter of the rod over in denominator for shearing acceptable shear. If we approach the problem likewise, instead of a rod inside a block, just go by a steel plate inside the rod. And so a steel plate of a thickness of a quarter of inches embedded in a concrete block to anchor a high strength cable, what you see here, and there is a pulling out force here applied here. The ultimate strength of the steel the steel plate has the ultimate strength of 36 ksi, and ultimate bonding stress is between two materials is 300 psi. the factor of safety for the entire system is provided to be 3.6, and a pulling out force equal to 2.5 kilopounds applied at the cable. What is the required width of the plate, and part B, what is the required length of the plate. Likewise, previous problem, what is the required sufficient length of the rod. We first, because this is a plate, we need to go with the width of the plate, then in part B comes to the length of the plate. Let's approach the problem. So in this problem, for part A, we are working with the outer part of the plate which sticks out of the concrete, and to calculate what is the width of the plate. So in part A, P failure is sigma failure times the area, and because of the nature of the pulling force and a hole in the steel plate, we need to go by a net cross-sectional area. So if this is A for the plate, this is the width, we call it A, cross-sectional area is nothing but a subtraction of A minus diameter of the hole times the thickness of the plate, which in our case is a quarter of inch. And also the same kind of force applies to a steel. Again, pull. And factor of safety is force of failure, P of failure, over acceptable P, which is the P, our problem statement. By expanding P failure, we can have rearrange the equation of factor of safety. That's nothing but sigma failure times net cross-sectional area A minus D times T over acceptable P, which is provided in problem statement. This is the same P, and by doing so, factor of safety times P is equal to sigma failure times open parenthesis A minus D close parenthesis times thickness of plate, and the only unknown here is A. If we arrange our equation based only on A, it just gives you A equal to D plus the rest of the equation. If you just replace the numeric value for that, D is the diameter is 3/4 of inch, which is the diameter of the hole is 3/4 of inch, which is provided, plus factor of safety for the entire system is 3.6 times pulling out force is 2.5, and over in denominator we do have sigma failure for a steel, which is 36, and the thickness of plate is 1/4 of inch, which is 0.25. If you do the mass, it gives you A equal the width of plate is equal to 1.75 inches. As soon as you know the width of the plate, likewise previous problem, you can just go on and calculate the required length of the plate. Let's see how that goes. So in part B, we take care about the embedded part. So definitely it goes by a interface of a friction between the steel and concrete. If you try to pull it out from the concrete, the friction contradicts it. So there is a friction, and there is two surfaces of that, the top surface and the bottom one. So we do have two of them, and also we do have the other areas, something like in sides. There is a friction at both sides, and if we want to show that, that's something like how you can see that here, and there is one at the rear. So part B, based on shear between plate and a slab. So you can see between the steel plate and a concrete slab, you can see the shear or friction area is 2 of top and bottom, and 2 at the sides. So this cross-sectional area is nothing but A, width of the plate, which we calculated to be 1.75 inches in previous step, times the length of the plate, which is unknown, B, 2 BT, plus 2 area at the site, which goes by again length of the embedded length of steel plate times the thickness of the plate. So that's 2bt. Sorry, 2bt stands for the blue one, the sides, and AB are the top and bottom surface. So if we arrange the area, it gives us 2b in bracket a plus t, close bracket. From data, we know tau failure, a bounding shear between the material is provided to be 300 psi, which is 0.3 ksi. And P failure this time is equal to tau failure times appropriated area, and it just comes from here. If you replace the area in the formula and you call it formula 1, on the other side we do know factor of safety against is P failure, our acceptable P, 1 equal to 2 gives you the key solution, the key to solving the only unknown of B. By rearranging the equation, B is equal to factor of safety times P over 2 tau failure times A plus T. Replacing the numeric value gives you required length of embedded length of a steel plate, and which is 7.5 inches.